We are ready to roll, Ellen. Thank you.
Okay, thank you very much for joining us for this webinar related to PVD coatings. And I'm delighted to welcome Jörg Jozik from Oerlikon Balzers. I'll just give you a quick introduction to Jörg. His talk is going to be called PVD Coatings as an Enabler for the Increasing Requirements in the Automotive Industry. Jörg studied physics at the Technical University of Kaiserslautern in Germany from 1992 to 1998, and in the meantime he also got an MBA at Trier, and in 1995, and then his PhD study was in physics at the Technical University of Kaiserslautern with the title Brilliant Light Scattering Spectroscopy in Dipolar Coupled Magnetic Structures, and he was awarded his PhD in 2001. Between 2001 and 2005, Jörg led the development laboratory of the Institute for Surface Analysis, IFOS, in Kaiserslautern. And in July 2005, he started at Oerlikon as a production manager for the automotive plant. In October 2006, he became a key account manager at Oerlikon. In December 2015, he became global head of sales automotive at Oerlikon. And then from April 2017 until today, he's been the technical business development manager at Oerlikon. So without further ado, Jörg, I'll pass over to you for your presentation.
Yes, thank you very much for the kind introduction, Alan, and thank you for the opportunity to do this presentation here. I hope you can see my screen now.
Fine.
So as Alan already mentioned, I want to introduce you a little bit to the requirements in the automotive industry and show you a little bit the development, what are the requirements from our customers and how we need to adjust the coatings respectively. Please allow me a few words about Oerlikon itself. Oerlikon is a Swiss-based company. Basically, we have two divisions. One is a Surface Solutions division and one is a Polymer Processing divisions. They are both similar with respect to the revenue, and we are serving globally our customers in a lot of different countries, North America, Europe, Asia, basically the product spectrum we have starts from nitriding to thin film coating and thermal spray, but also component manufacturing and additive manufacturing. Today I would like to discuss in more detail the thin film coating, the PVD coating, and for our automotive centers, we have globally dedicated automotive centers. We are also based globally based on our customers' location. So mainly North America, South America, different centers in Europe and also in Asia. For next year, we are also planning to open a new center in Mexico due to some customer requests. So let me start a little bit about the PVD coating. So typically when we discuss the PVD coating and the type of coating with our customers, we would like to understand the tribological system. And that does not only include the counterbody, so that means the actual part against which the coated component is running. Here we have a piston pin, for example, sitting in the piston, but also we would like to understand what kind of surface material do we have, how is it prepared, and what is the surface condition, because we see that for the tribological behavior, also the surface condition and the interaction of the different materials are an important point. And so based on this information, we typically suggest a type of PVD coating to the customer. And this is kind of adjusted with respect to the actual application. And this allows us to really do a tailor-made solution for each application to match the customer needs as required. We serve a lot of different application fields. It all started in the fuel injection systems. Here it started with diesel, and I will speak in more detail about this to explain you the development there, but also valve train components are coated. Now with the increasing requirements for the exhaust gas regulations, also exhaust gas components and after gas treatment components are treated. Of course, engine components in general. For electrification, there's a new field, and I will also show you a few examples about this, which is the differentials for the shafts in the differentials, where some kind of electroless nickel surface treatment is replaced by a PVD coating. And we also have turbochargers because of the increasing temperatures and the hydraulic safety components, which become more and more important in the vehicles. If you think about autonomous driving, for example, then those type of components are taking over more and more actions, and their wear becomes also an important topic. So in general, why would an automotive customer use a PVD coating? First, when it all started in injection systems, it was to reduce wear in the actual application and friction. So that was basically where it all started. And one of the benefits was that the PVD coating can also comply to very tight tolerances, which are given especially for the injection components, where you have only a few micron of space between the actual component and the housing. And of course, the component needs to operate in such a condition. Now we see with the trend to downsizing that the loads to the respective components are increasing further and further. That means the need for surface protection, wear protection, becomes more and more a topic where the customer need our help. Beside that, the temperatures are increasing, especially for the exhaust gas system, where the requirements are constantly increasing, as I already mentioned. And another topic that is discussed, however, right now it's a little bit pushed out again, is the replacement of this hexavalent chromium with the REACH regulation, where the PVD can also be a good alternative to protect the surfaces. All over, for the automotive industry, always cost is one of the major drivers. And we also have certain examples where we were able to show to our customers that applying a PVD coating allows them to lower the cost of the complete system. One important temperature aspect when we talk about the coating solution with our customer is also the application temperature range. For different application temperatures, there are different type of coating families. It's not one dedicated coating, it's really a family. So for the low temperature coating area, we have the family of the carbon-based coatings, which are widely used for many, many applications. However, this only works up to 350, 300 degree. Then we will have the graphitization of the diamond-like structure, and this allows the coating not to survive this higher application temperature. So if we move above this temperature, we can choose from the family of the nitride-based coatings, which work pretty well up to 800, 850 degree. And if the temperature is even above that, we can look at the oxide-based coatings. Starting with the family of the carbon-based coatings, we can distinguish those between the hydrogen-free and the hydrogenated carbon-based coatings. And here's a small excerpt from what Oerlikon is offering with the brand names like Bali Q Carbos, Bali 4T, which is a TAC, and I will show you an example about this later, and the DLC Star, which is a hydrogenated AC, which is widely used also for the a lot of applications. We have some cross sections here where you see a little bit the difference. You see that most of the coatings are very smooth because they are applied with the PVD coating technology. The TAC coating, you see this structure here is slightly different, and that is because it has a different type of deposition method. Here we use a so-called arc evaporation process, where we have a high energetic arc evaporating the target material, and this leads to certain droplets in the surface which require some surface treatment after the coating, so that the coating can work in the respective application. One important thing to point out for the diamond-like carbon coatings is this temperature limit and the graphitization, where the very stable diamond structure then is converting into the graphite structure. And this goes with temperature and also is depending on the actual application pressure. And that is basically one of the reasons why the application is limited or in temperature for the carbon-based coatings. So, however, I said in the beginning, we try to tailor the coating with respect to the customer application. That can easily be done by playing with this ratio of SP2 and SP3 to, for example, influence the hardness or coefficient of friction, or we can add different doping elements so that we can impact the properties like coefficient of friction or wear coefficient, also have an impact on the stability, chemical stability towards additives. So one important thing, especially for the carbon-based coatings, is the so-called running in behavior. And this is, if you think about the surface that is coated, and the coating is just following the actual surface in the initial contact with the counterbody, you will have the first contact at the roughness peaks, and there we will have this kind of graphitization, which is first smoothening the tribological system and also transferring a little bit of graphite to the counterpart. And by this running in behavior, we are preparing the tribological system. This is one of the major mechanisms how these carbon-based coatings are working. And if this has happened, then we will have the stable system for the rest of the lifetime. And we looked a little bit into that for the application of piston pins. Here we have a piston pin that was coated with a DLC coating. It was put into an engine, and after 400 hours, we took out the piston pin and had a look at this area. So we saw areas that appeared more shiny and others that appeared more dull. If you look under the microscope, you see different areas, one where the load was applied and where this running in has happened, and you have a rather smooth area here, and the other area, the more dull area, where the load was not applied and where the coating as deposited. And we were, of course, interested in understanding how much of the coating is used up for this kind of running in. And if we think typical coating thickness are around 2.5 micron total coating thickness. So what we did is we measured the coating thickness along this line, and we found that there was a difference from this area to this from 0.1 to 0.3 micron. So that means for this running in behavior, approximately 10% of the total coating thickness was used up. So let's look a little bit, as I mentioned, about the history of the application from the automotive requirements from our customers. And I mentioned already that the coating was first applied with the injection systems, and it started with diesel. And here one of the major trends was the increasing injection pressure. And at a certain point, when the injection pressures were around 1,800 bar, the wear of the components became so huge, especially for the needle, that the sealing area needed to be coated. And as the pressures of the injection were further increasing, and right now we are typically at 2,500 bar, some systems are even higher, this is something that is still needed. And the same trend basically is also can be observed for the gasoline injection. Here we saw that for the pump, around 200 bars, when the 200 bar system came up, that the pump piston needed a coating because it was wearing, and moving further up with the pressure as the development was ongoing, we also saw that the needles, so that means the sealing area of the injector, also needed a coating. And here's some example from a diesel injector needle, how it looks like. So here you see this typical wear step, which is happening if the coating is not present. And here you see that it is this 2,800 bar from an actual needle. So typical components that we are coating for the diesel and gasoline, again, is the needles from the injection systems, pump parts different, and also for natural gas. However, here the pressures are much lower, and here it's more kind of friction reduction. And similar parts to a diesel pump can also be used for the hydrogen combustion engine or natural gas injection systems, which are one of the topics that are discussed, especially for the commercial vehicles, in order to reduce the CO2 emission. So another thing where the automotive industry was requiring modification of the actual coatings, and how we try to support this is with the piston pin. Here, the standard coating solution is a DLC star. And depending on the actual requirement, we can use this hydrogenated amorphous carbon coating with some kind of support layer. And that is really the standard for the high volume solution that we are offering globally. However, for some other or higher requirements, we also have this TAC, which is a new coating. Here you see again, because we use the arc evaporation process for this, as deposited, you see a quite rough surface, and after some post-treatment, this surface is much smoother. So that is the new requirement, and due to the higher loads in the systems and less lubrication or lower viscosity oils, this is something which is now coming up and which the customers are requiring. We also have another type of coating, which is a nitride-based coating. It's a molybdenum nitride. And this is also used in serial production, but this is for some very special solution, high performance applications, where this is really used as a very temperature stable product. So you can go higher in temperature compared to the 300 degree, and this coating still survives it. And there's another case when this molybdenum nitride is can be used very well, and that is if some of the DLC coatings can interact with some of the additives in the lubricant. And here I show you an example later that how the additives can interact with the PVD coating. And for this case also, molybdenum nitride can be a suitable solution, but I will show you more details about that a little later. So, so far we talked a lot about combustion engine, but right now, of course, everybody's talking e-mobility. So also parts from the electric vehicles are coated, and I already mentioned here the differential shaft. For this application, typically the majority of the parts got a different surface treatment, electroless nickel, and due to the increasing torques and higher loads, this is somehow limited, so that for the electromobility especially, more and more PVD coatings are used. And this is again a DLC star or a titanium nitride. And you see also here in this simulation that this shaft is a very is highly bent, so it's a very dynamic component, so that the coating also needs to be able to perform under these kind of harsh conditions. Here we also offer a kind of combined treatment where we combine nitriding the part with a PVD coating, and that is also a very good solution in case of very high loads. Some of our customers, they experience that the PVD coating is cracking because of the high load. The surface is deformed so much that also the base material might be damaged. And in this case, if we have this kind of duplex treatment like nitriding plus PVD coating, where we have the nitriding first with the diffusion zone, so we have a medium hardness here already, then the compound layer on top with a higher hardness, and then on top we add the actual PVD coating, which allows us to have a smoother transient in the hardness profile, if you think here about from the substrate hardness down to the typical coating hardness of such a DLC coating of 20-25 gigapascal typically, and then this enables the component even to work under a higher load. Limits of carbon-based coatings. I already talked about temperature, and here we always have this graphitization, especially as soon as we have the carbon-based coating, the DLC structure and the sp3 bonding that is converted to the graphite bonding. We can also have examples where the load is getting too high. Here we can shift the border a little bit by applying a harder carbon-based coating. So using a TAC, a hydrogen very hard coating compared to the PVD coating or additives. And please allow me to go a little bit deeper into the additives, because here we did a test. This test was quite simple. So basically we coated a disc or a pin, a disc, and then we put a pin on this, and then we had this reciprocal wear test, which is a kind of standard test. And we used different type of oils, and we had a look at the wear track, and here's a picture on the wear track, and then we measured the profile across the wear track, which is displayed here. So let's start with a dark gray line. Basically, this is the standard DLC coating with a standard lubricant. And after this test, you see, okay, in the area where the pin was moving, you see some traces, but not really wear. It's just a smoothing of the coating. And if you measure across this profile, you do not see anything very interesting. Yeah. So the situation changes completely now if we use a different kind of oil, which has a high concentration of MODTC in the lubricant. And if we then repeat the same test again with a amorphous carbon coating, a hydrogenated amorphous carbon coating, we see a significant a change in the behavior. We see a deep wear pattern, and if we measure across this wear track, we see clearly that the wear goes down to the substrate. And here you see how the MODTC is chemically attacking the hydrogenated amorphous carbon coating and leads to this very severe wear. And in order to address this, we applied the molybdenum nitride coating, which are the other two graphs here. Again, one with a standard lubricant and one with a lubricant with the high concentration of the MODTC. And here, looking at the wear track, you see that this behavior is more comparable to what we see here with a DLC with a standard lubricant. So in case the additives are concerned, then the molybdenum nitride can be an alternative to the carbon-based coatings. And that is one of the reasons why it was used for this special piston pin application. Okay, so let's move up a little bit higher in the temperature range and talk a little bit about oxide-based coatings. So the oxide-based coatings are used as a kind of oxidation barrier. And we also have this in serial production in order to protect the piston crown. And here the issue is, and this is a kind of test we did together with one of our customers, Mahle, where the piston crown was coated, and then this piston was put into an annealing ambient atmosphere at 600 degrees C for 3000 hours. And in the area where the coating was applied, you see that there's no oxide layer building up, but the other uncoated area show how the oxide layer is being built. And that again gives a good example or shows nicely how those quite thin coatings can even protect the parts against a high temperature impact. That is also a solution which is in serial production for some special application and also can be used for the hydrogen internal combustion engine. Let me now speak a little bit about a kind of new topic. And here we want to use a PVD coating, which is classically helping in the application to protect parts against wear or to reduce friction. But now we are also thinking about adding some additional functionality in order to be able to measure data, to get new data. And then we want to use this PVD coating to build a sensor. And the idea here is that the classical coating, nitride-based or carbon-based coating, is used for wear protection, but it's only helping the system to survive the application. But you do not get any kind of feedback from the system directly. You just see in the end it has worked or it did not work. Yeah. If you now think about a feedback loop, then the idea is that the coating, on one hand, of course, should continue to protect the component, but on the other hand, it should also be used to give some information back from the actual system and allows, for example, to adjust certain operation parameters or can be used for predictive maintenance or whatever. Yeah? And therefore, the idea of a thin film sensor, which is combined with a raw part plus some electronics to read out the data, can be used to build up smart components. That means by using this kind of embedded film sensor, we can have some real-time monitoring. As I said, for predictive maintenance, this can be used. We can adjust certain parameters for the application, and so this can be very beneficial. And because it's a thin film sensor, it does not need a lot of space. So also sometimes it's a question of a room where to place a sensor. and the engineers often do not have the chance to allow some additional space, but the thin film coating can be, in this case, a very useful tool. If we look at the kind of sensors where the coating can be used, basically we can use it for acoustic or for vibration, for force and pressure measurement, and I will show you examples about this, and also temperature measurement. Basically, it's also something, technical feasibility would also be there for chemical analysis or for electric field, but currently we are working on temperature, force measurement, and vibration, which is also similar to kind of force. So how does it work? So again, we start with a component itself as a substrate, and then we have our sensor coating. Basically, this is also a kind of carbon-based coating, because carbon-based coatings are also kind of dielectric. They have some dielectric property or piezoelectric properties. So by applying a force or current, you will get a response from the system, which can be measured. So we connect this via wires, and then we can read it out in a classical connection, or we can use a transmitting device which can send then the data outside. In order to allow this, we need to decouple this sensing element from the substrate, because typically this is a kind of a metal part. So we need to have kind of insulating layer first before applying the sensor, and then a kind of top layer to cover the sensor, and then we can even add a tribological coating. So here are some examples of this. For example, for the force measurement. So here we had a contact area where force can be applied, and we have the sensoric element here. These are the connectors. And if I now compare the response of this sensoric film compared to a classical sensor, you see that, first of all, it's very linear with respect to the force, which is here on the x-axis, but also that it is more sensitive than the actual, than the classical sensor. So it allows you very sensitive to detect these changes in force. So that is one very interesting thing. Looking at temperature measurement, again, what we did here, we had here our sensor. So Diarc Senso is the brand name for this coating. Was applied here in a water tube, in a tube where water was flowing through, and we compared it with a classical PT100 element, and then we looked at the response again, and we see again that the coating sensor is responding much faster to the temperature change here from the water compared to the classical sensor. So that means not only more sensitive, as here seen by the force measurement, but also a faster response time. And you can also see this here in another example where we have a flashlight. And if you switch this on, basically you also get a very fast response from the sensor coating, which is only 6 microseconds, while other sensing elements take much longer. So that is something which we are currently evaluating, and which opens completely new field of application also for us and for our customers. Let me summarize my presentation. I hope I could show you with some application examples that the carbon-based coatings are widely used, and they are used already for many decades, and there are also adjustments based on the increasing requirements, like harder coating, as we see, for example, for this harder carbon-based coating, the TAC coating, which is can be used for higher loads. The new and increasing requirements can be addressed by adjusting the coating architecture or the type of coating. That is also driven by the market. also new fields in the automotive industry, like the e-mobility. They can, the coating can be applied to support those where other classical surface treatments are not enough. And with these smart coatings or sensor coatings, new fields of application are open, where data can be measured in areas where it was not possible before, with a very fast response time and very sensitive. So that brings me to the end of my presentation. Thank you very much. And yeah, I'm still here for some questions.
Thank you very much, Jörg. That was very interesting. We have a few questions in the chat. So I'll ask you these first of all. First question, does the substrate require preheating before depositing the coating material?
Well, we have a vacuum process, and part of our in the initial steps of the coating, we also do a kind of heating after the vacuum was created. However, this is more to evaporate any water that still might be deposited on the part, because we have to bring it from an atmosphere into the vacuum, and in order to let the water evaporate faster, we heat it up, typically the substrates to a range of 100–150 degrees C before we start the actual coating process. So if that is meant with preheating, yes, we do this as part of the coating process. Okay. And typically the parts we are coating also have seen a heat treatment process before the coating. So that is also something we need to consider, because the heat treatment is, or annealing process is running at certain temperatures. And of course, we want to stay with our coating temperature below the annealing temperature, not in order to have another heat treatment of the actual component.
Thank you. Next question, would you be able to provide a brief overview of the decorative PVD coating? And he calls that EPVD, which I'm not familiar with that terminology, but that's what he says you call it, that is being used in automotive applications.
Yes. That is also something we offer. I'm not a big specialist in this, but I'm very happy to connect you to our experts in case you can forward the contact to me. Basically, this is also part of the hexavalent chromium replacement. And here some plastic parts are also coated for decorative purposes. Then basically you have a thin, for example, chrome layer that you apply, and then you still apply a sealing layer so that the chromium layer is kind of conserved. Also, loudspeaker grids are coated with the PVD technology for decorative purposes. I cannot give a deep or a real overview in this, but I think we can discuss this offline. Yeah, so that is something we offer, and I'm happy to provide more information. I do not have it at hand right now.
Maybe the best thing, if the person asking the question could send their email to Pamela, then that could be, we can put you in contact. Did you put your email address on any of the slides at all?
Yes, my email address is on the very first slide.
Right, that's great. Yeah.
So I can also show this for the discussion. Then you have it. So here you see it in this area.
That's great. So people can ask you directly that kind of question. Okay, next question. Have you any experience of controlling or preventing the blistering of carbon-based coatings, as in engine tappets, caused by rolling, sliding, contact fatigue, and many millions of stress cycles?
Yes. I mean, here, this is, we have some experience here, and this is always, or goes along a little bit with the question of surface preparation also, that you also need to do some kind of polishing before you apply the actual coating, in order to enable the system to survive over the lifetime. And moreover, we do not use just the diamond-like carbon coating. It's a multi-layer coating. We have a ductile coating underneath in order to support the or help the DLC coating to bear those different kind of loads. And in our case, we use chromium nitride. Some of our competitors, they use a tungsten carbide coating, but typically there's a kind of ductile underlayer before the actual DLC coating.
Okay, thanks very much, Jörg. Another question. Regarding the strain sensor, are these temperature and strain sensors already used in automotive industry, or are they still in development?
This is a kind of new development where we have some customers who are developing the first application with us. We do not have this in serial production yet. It is upcoming. It is used, those kind of sensors, for a few applications, for example, for measuring the weight in certain bearings. That are some kind of demonstrators where this is used in for automotive, for example.
Okay. You know, when you sell such a coating to an auto producer, very often they like to dual source their coatings, don't they? They don't, very often they won't just have one supplier. They prefer more than one. Is that any issue at all for you or for your competitors?
And no, I mean, of course, this competition is there. And I mean, all we can do is convince the customer with certain arguments like high reliable quality, like global services, standardized processes globally, so that, for example, if he gets one part in Europe, he will get exactly the same part in Asia, so that the processes for the coating and or the pre and post treatment are the same. That is something which our customers value quite high, and that helps us to have a certain share of the cake. Of course, as you mentioned correctly, it is usually unlikely that there's only one coating supplier. Typically, it's a dual source, yeah. And there, I mean, you can play a little bit around with the share. If you have better arguments, it's not 50-50, then it might be changed towards your favor if you are in favor of the customer. But in general, this is right. Typically, there are several sources. And for example, piston pin, it's a commodity business. So all big coating suppliers are approved by all the OEMs, and then it depends on pricing, availability, capacity, and a lot of things. But I mean, that's just a part of the game, yeah.
Yeah, very interesting. I've got a few questions. When you talk about the need for the transfer layer and the benefit of the transfer layer, and in fact, I think it's a requirement, isn't it, for many tribological applications for you to develop a transfer layer?
Mm-hmm. Yeah.
So what's the difference between coating both surfaces compared to relying on the transfer layer?
I mean, for most of the applications, we see that coating only one component is already enough. And I mean, for automotive, as this is always cost sensitive, very often that is really the case that only one side of the tribological system is coated. However, there are applications where both components which are in tribological contacts are coated, and then typically we choose the coatings for both sides slightly different, so that there's at least a difference in hardness, so that one part can always be used to do this running in, and then the other just helps to stabilize the system. But especially for the carbon-based coatings, this running in is essential for the tribological performance.
Yeah. Excellent. You talked a lot about diesel engines and parts in diesel engines, but of course we believe that diesel engines are becoming obsolete. So they tell us. And many cities are banning diesel cars from even entering the city. How do you see this affecting your business going forwards? Do you think that banning of diesels is going to continue, or do you think that diesels will come back in?
Well, I mean, we were all told stop doing diesel, yeah.
Yeah.
But on the other hand, nobody told us, okay, what should be it? What should replace it? Yeah. So some think of e-mobility.
Yeah, we've. I don't know. Carry on.
And I think, yeah, this is really the open question. So I believe that the share of diesel will decrease over time, but what will take over, I think, is not complete.
Yeah. I don't know about everybody else, but I keep losing your voice actually. But I mean, obviously diesels are becoming more efficient.
Natural gas or a hydrogen combustion engine in order to reduce the CO2 footprint. Yeah.
Yeah.
I think all the customers I'm in discussion with, they are not relying on one source only. So they are playing in more or less all the fields. And I think the race is not won for one or the other technology yet. I mean, for sure, I agree that at least the diesel share will go down. We will see if it will vanish completely or there will be a small share surviving. But the alternatives are for sure coming.
Yeah. And it depends on the application, whether it's a truck or even a ship or whatever, there will be there will be different application trends in different sizes of parts as well.
Yeah.
You talked about using the arc technique for the TAC coatings.
Yes.
Do arc droplets represent a problem in that application?
Yes, and I mean, the issue with the droplets basically is that they actually have the same hardness as the coating itself. So if you would not somehow avoid the droplets or do some post-treatment to smoothen the surface, you will just destroy your counterpart. So there are different type of philosophies in the market. Some are using filtered arc processes, but then the deposition rate is going down because you have this filtering device, and depending on how much you filter, you get a smooth coating, but it will grow very slowly. Or you do it fast with a lot of droplets, and then you have to put more efforts into the post-treatment. So we have both technologies, filtered and unfiltered, in Oerlikon, and depending on the application, we rather use one or the other. But really, for the arc evaporation process, you have to do this either this filtering or the post-treatment in order to create a stable tribological system and not to destroy the counterbody.
Thank you. Balsas were one of the first to incorporate electron beam evaporation, weren't they? And I think they went more to arc and to sputter. Do you still see a future for electron beam at all?
Yes. I mean, the electron beam evaporation is very good if you look for very smooth coatings. So there are certain fields, especially in semiconductor applications, where this is really one of the major requirements. And here, this technology, I think, will continue. But for other applications, the sputtering or PVD or arc evaporation all will be are more productive, let's say, because again, here we have larger vessels. We have by this then lower costs, which is more attractive for the customers.
And of course, there's less heat loss to the cooling water in the EB-PVD technique.
Yes.
Compared to sputtering, for example.
Yes, right.
Has anybody done a kind of cost comparison on that?
I'm not aware about that.
You know, in terms of process efficiency.
Yeah, I'm not aware about that. However, what we did, and that is quite interesting, and a new requirement also from our automotive customers, we have now done a calculation of the CO2 footprint per part we are coating, because that is coming up more and more from the industry, that the customers are requesting, okay, what is the impact with respect of CO2? And so also within Oerlikon, there's I mean, of course, the focus is also sustainability. And by doing this calculation, I think this allows us also to see what are, let's say, the parts that have a better CO2 footprint compared to others. And but also by collecting all the data from the processes, this allows us to steer the processes also differently and more efficiently if you think about sustainability. And that is something which is now coming up more and more. I mean, the data are available already for a long time, because all the coating machines, they track all the data, the process parameters, of course. But there was not, in the past, not a lot has been done with this data, which were available, of course. But now this has changed with the the artificial intelligence. The data are reviewed, and there are certain critical things discovered, and this allows us then also to optimize the processes and work on these issues.
Thanks, Jörg. You know, you showed the deflection of the piston pin, the deformation, and also the pinion shaft.
Yes.
What kind of deflections are you seeing? You know, what's the order of those deflections? Is it tens of microns, or microns, or hundreds of microns, or what?
No, it's really maybe let's see if we see it here in this slide. Piston pin. Here it was. This here is some 100 micron, for example.
Right. Okay. That is many times greater than the coating thickness.
Yes, right.
For example.
And, I mean, it's really, if you think about the piston pin sitting here in the piston, and then you have the conrod moving it up and down, it's really bent very, very much, and there's a heavy load. So it's really also kind of a deformation that you see there. And it's similar also to the differential shaft, and that is also the reason why these, let's say, electroless nickel coatings are not working, because the deformation is just becoming too large.
Yeah.
So this is really something where the PVD coatings show an excellent behavior, and also because you have this, not only this very hard surface, but you also have this ductile coating underneath that helps us to survive this kind of harsh applications. Because I mean, basically you have this very hard and of course also brittle DLC like coating on the surface, and then you do these wild things with that. And if you would not support it underneath, and we saw that in the very beginning when we had a simple coating architecture without this ductile interlayer, you will have cracks in the DLC coating, and then the DLC coating will also start to peel off. And that is exactly the reason why this coating architecture was adapted, in order to help the component survive, or the coating survive.
Yeah, that's very interesting. I've always thought that people don't really think about the wider deformations. You know, even under a static contact on a coating, the substrate deformation can be much greater than the coating thickness.
Yes.
And people just forget about it.
Yeah.
Okay, very interesting. My final question was about your lubricant tests with the nitride coatings.
Yes.
Were both of those surfaces coated?
We only coated this disc. The pin was uncoated.
Right. Yeah.
So it was a classical 100 chromium 6 ball that is usually used for this kind of wear tests, and only the disc here was coated.
Yeah. Okay. Well, I don't have any more questions, Jörg. That was fascinating and very interesting. I don't think there are any more Q&As in the chat. So I'd just like to thank you finally, Jörg, for giving this talk and revealing so many interesting aspects of coatings, particularly for automotive. But I'm sure that these learnings are valid in other applications as well as automotive, many of them.
That is right, yes. Okay.
Yeah.